All right, so let's get things started here. So as I mentioned, Guy Frankenfield with DN Tanks is going to be our presenter today. We do have our senior project engineer, Lonnie Russell, on the presentation as well, so he might be part of it. But I will pass the mic over to Guy and let him take it away.
Oh, thank you, Tyler. I appreciate it. I hope everyone can hear me well, and you can see the screen in front of you that says thermal energy storage. We've been in this business for almost 40 years, building thermal energy storage tanks across the country. And I'm a mechanical engineer. I've been doing this for DN Tanks for over 15 years. So I have a lot of knowledge about this industry and would be happy to answer questions at the end, as Tyler mentioned. But I'm going to jump right into it. And when we talk about energy storage, it's storing energy during off-peak periods and then distributing that energy during peak periods of time. And we're all familiar with energy storage type systems. We have hot water heaters in our house. We make ice cubes in our refrigerators. We utilize batteries in almost every type of device anymore, especially our smartphones, where we charge them up at night and then we discharge those batteries during the day. And the most complex energy storage system is the human body. But we're not going to talk about any of those. Today we're going to talk about thermal energy storage, and in most of the slides and information have to do with chilled water or hot water thermal storage systems. I always like to start at a very high level and bring it then down to the thermal storage technology. And at the high level, it's important to understand a little bit or think about our electric grid, which has been evolving over decades of time. And it's a very complicated electric distribution system where there are multiple ways of generating electrical power and then pushing those electrons onto the grid so that we can use them. So across the top of your screen, you see the many different ways that electricity is generated today. And at any one time, there could be a dozen different types of electrical production systems out there pushing that electricity onto the grid. It's distributed then through miles of wiring, and then we use it in our homes, we use it in businesses, and we use it in industrial and commercial applications. But what's happening with our grid, it continues to evolve, and today the big evolution is with adding renewable type of power generation systems to that grid. And renewable, the two biggest type of renewable generation that is being added right now are wind and solar type power generation. And with either one of these two types of renewable generation systems, it's an intermittent type generation, meaning when the wind blows, it generates power. But when the wind stops blowing, it doesn't generate power. Same with solar. When the sun is shining, it generates power. And when it's not shining, it doesn't. So because those are intermittent and they can't be turned on 24/7, that means that the more you add this type of intermittent power generation to our grid, the more energy storage systems we're going to need in the form of batteries or thermal storage or others. So what are those types of grid scale energy storage technologies? There's pumped hydro and battery storage. In California, there's several pumped hydro systems where there's a lake on the top of a hill and water runs down through a turbine, generates electricity, and is collected down below in another lake. And then at nighttime, that water is pumped back up into the upper lake, and then that pumped hydro system again generates power during the daytime. Battery systems, there's lithium ion systems by many different manufacturers now have grid scale type battery systems. There's compressed air, flywheels. These are other type of grid scale level energy storage systems. And then there's also thermal energy storage. And as I mentioned, this has been around for 40 years. We've been building chilled water or ice type thermal storage systems that store the energy in the form of cold water. And that cold water is a virtual battery of energy that is being stored so that it can be used during those peak periods of time. So when you're comparing those different types of energy storage systems, those grid scale type systems, and you're looking at pumped hydro or batteries or flywheels, compressed air, Department of Energy just recently submitted a report in July of 2019, and you can see the comparative efficiencies of those technologies, the expected useful life of those technologies, and the capital costs associated with those type of technologies. And when you compare it to the bottom row, which is chilled water thermal storage, the chilled water thermal storage is more efficient, it's got a longer useful life, and is typically lower in first cost than any of those other type of energy storage systems. So when there's an opportunity for an owner or an engineer to consider energy storage, one of the first ones that should be looked at is thermal storage. How can I utilize thermal energy storage in my systems? The best way to do it is if there is a chilled water district cooling system associated with a facility or a campus. And that is in the center of the presentation. You're looking at a chilled water cooling plant, and that is providing chilled water with very large horsepower chillers. It pumps that chilled water out to the building or the campus. That cold water then is used for cooling or processes, and it returns back to that central plant for recooling again. So it's a closed loop chilled water system that could possibly use a thermal storage tank. The tank can be added to that system, and it acts like a virtual battery. It allows the owner or the operator to run their very high horsepower equipment, the chillers, the pumps, the cooling towers. It allows them to run them when it's most beneficial to them. Typically, that's during off-peak hours or nighttime when it's cooler ambient conditions outside and a lower cost of power. They can run that equipment. They can store water in that tank, and then during the daytime, utilize that cold water that's been stored in the tank for cooling their building or their campus. And every one of the thermal energy storage tanks that we've ever built over the last 40 years, it had to have some sort of financial benefit for that owner. And I'm listing here several of those types of benefits, those financial benefits that owners seek out or recognize when they add a thermal storage tank to their system. There's usually an energy cost savings component of that, where the owner has a time of use electric rate where they have lower cost of power during off-peak hours, where they could run their chiller equipment during that off-peak hours at a lower cost, and then turn off their equipment during the peak time of the day. That usually saves both on the KW, the demand side of their electric bill, and the KWH consumption side of their bill. Also, many times an owner is looking to replace or add a chiller to their central plant system. Perhaps they have an old chiller that needs to be replaced, or they're expanding their campus. And when they're looking at replacing or adding a chiller, that's the perfect time for them to consider, instead of adding that refrigeration equipment, perhaps I should add a thermal storage tank. We're going to look at an example of that later in this presentation, and it's a very economically beneficial way to consider adding a tank to a system. The last thing on this particular slide is resiliency. By adding a thermal storage tank to a campus, the owner is getting the fringe benefit of this very large reservoir of chilled water now on campus that could be used for backing up their cooling system in case their chillers go offline unexpectedly, or the tank could be used as a dual purpose tank where the cold water in the tank could be used to help put out a fire in case that were the case at the campus. So those are some of the benefits of thermal energy storage. Electrically, let's look at what happens, how a thermal storage tank helps the owner reduce their electrical costs. A typical electric load at a facility or a campus looks like a bell-shaped curve. On here, the electric load, you can see the bell shape or the electric load rise up during the day. And a lot of that electric load during the day is due to the cooling system. And that's because the campus is being now occupied and it's warmer and ambient conditions outside, so their space cooling requirement goes up. And so there's more electric load during the middle of the day, typically during the middle of the day. If an owner were to add a thermal energy storage tank to their system, they could permanently reduce that electric load that they would consume during the day, because now they have the opportunity to run their high horsepower chillers and pumps at nighttime to cool that water, and then during the daytime they would have lower horsepower pumps pushing that water out to the campus for cooling, and they would be able to de-energize their chillers and cooling towers. So there's a permanent electric load reduction capability that they would see at their facility or campus. And in addition to that, there is a consumption reduction for that campus. So if they're producing the cold water at nighttime and storing it in that tank, they're actually running their chilled water system when it's cooler ambient conditions outside. And when it is, that's typically the chillers will run more efficiently when they're condensing at a lower ambient condition outside. So that reduces the kWh consumed to produce all those gallons of cold water. So there's a twofold benefit when you're utilizing chilled water thermal storage on both the kW demand side of the equation and kWh consumption side of the equation. And if the campus is going through an expansion, the owner has an opportunity to either add additional refrigeration equipment, cooling equipment, like a chiller and cooling tower, to provide that additional cooling for the campus, or perhaps they have already excess cooling capacity in their central plant at nighttime. And then instead of adding that refrigeration equipment, which you see on the left, they could add a tank, which you see on the right. And that tank has no moving parts. It has no horsepower pumps driving refrigerant. It is just a tank, a reservoir to hold cold water. So there's very little maintenance, if any, with a tank compared to the refrigeration equipment on the left. So there's a significant operation and maintenance reduction to when you compare a tank to adding more chillers or cooling towers to a system. And on the resiliency side, on the upper part of this presentation, It's an example of data centers, which have many of our data centers, like Google and Apple and AOL. They have very large data centers with servers inside that are giving off heat all the time, and they need to be cooled all the time. And you can see by the thermal image in the upper right that there's a lot of heat given off by those servers. Well, if their central plant system ever goes down unexpectedly, they have a reservoir of chill water in their thermal storage tank that could be used immediately for cooling and keeping that data center online. So it's a tremendous benefit for data centers to have that insurance policy and that resiliency of a thermal storage tank in their cooling system. And the picture below shows one of our thermal storage tanks with a fire hose nozzle connection on the outside of the tank. And that connection can be used by a fire truck. If there's a situation where there's a fire at a facility or a campus, a fire truck could pull up to this tank, draw water out of the tank, and use it to put out the fire. And many times that is a benefit to the owner, not only to have that reservoir of water available, but it could reduce their insurance premiums just by having that nozzle connected to their tank. Well, let's look at how a typical system would operate. This is a schematic of the typical chillers in a central plant. They're turned on during off-peak hours. They're producing cold water, which you see in blue, and that water is cooling the campus while simultaneously charging up or providing cold water to that thermal energy storage tank. Then during off-peak hours, the chillers, either one or more of the chillers, are turned off, and that cold water in the tank is drawn out of there through a pump, and it's pushed into the campus for cooling the campus. So that cold water in the tank now, that energy that's been stored in that water is now provided to the campus, and the warmer water returns back to the thermal energy storage tank. So inside the tank, there are actually two bodies of water in that tank. They're not separated by anything other than the fact that the colder water, shown in blue here, is denser and is going to want to stay at the bottom of the tank, and the warm water at the top of the tank will stay at the top, and the two bodies of water will remain relatively isolated from each other and stratified within the tank. So that's how it works schematically. I'm going to now show you a little illustration of what goes on a daily basis. At night, chillers are on, cooling the campus and charging the tank. Then during the daytime, the chillers are turned off, and that cold water is removed from the tank, and it provides cooling to the buildings. And that charging and discharging, that's a typical operation that happens every day, where at night or during off-peak hours, the tank is charged up, and then during the daytime or peak hours, that cold water provides the cooling for the campus. And inside the tank, the cold and warm return water is stratified in there. This is, you're looking through the side wall of one of our tanks, and inside the tank, we have specially designed a network of piping or a plate type diffuser system inside the tank that takes that cold water or cold or warm water that's entering or leaving the tank, and it takes that and it slows it down over the cross-sectional area of the tank. So on the right-hand side of the tank, you can see where the piping comes into the tank. The warm water will rise up through the upper diffuser, branch off, and in this case, hit an octagonal ring with slots cut in it. And that's where the chilled water enters and leaves the tank through the upper diffuser or a mirror image on the lower diffuser inside the tank. And that piping inside the tank is specially designed to take that flow rate, slow it down near laminar flow, spread it out over the cross-sectional area of the tank so that it's not mixing up those two bodies of water, so that the cold water stays at the bottom and the warm water stays at the top of the tank. This is a snapshot of one of the thermal energy storage tanks that we have at a customer in Virginia. And I've color coded the bottom region of the tank where that's the supply water, and the red at the top is the warm return water in the tank. And on the right-hand side, you are looking at the temperature sensors, the 11 temperature sensors that are mounted inside of the tank. And each of those temperature sensors represent the temperature of the cold water at that elevation in the tank. So you can see in the blue region of the tank, all those sensors were reading 41 degrees Fahrenheit. That was the cold water temperature that tank was charged up at nighttime. At the top of the tank, all those temperature sensors were reading 53 degrees Fahrenheit, and that was the return water temperature coming back to the tank. And you can see how distinctly isolated they were from each other and stratified within that tank. And the only temperature sensor, the one represented by temperature sensor number 7, that's the only one that is measuring anything other than 41 or 53 degrees. It's measuring 48 degrees, and that is in the region called the thermocline, which is the boundary layer in between the supply and the return water temperatures. And that thermocline is what the operators can watch as it slowly drops down through the tank when they are using the cold water. They're pulling that cold water out of the bottom of the tank and using it to cooling the building, so that as they're using it, that thermocline is going to slowly drop down through the tank, and that's how they will know how much cold water is still left in the tank. So where have we built these thermal storage tanks around the country? Well, owners like colleges and universities, there are many thermal storage tanks at these type. Across the top row, you're looking at the University of Texas, Cypress College, the University of Central Florida. These are just some of the college campuses that have thermal energy storage tanks. In the middle row, you're looking at government and municipalities like Lackland Air Force Base, San Antonio Airport, and in downtown Raleigh, North Carolina, in the legislative district. And in the bottom row, you're looking at hospitals, data centers, and power plants. And so anywhere there is a large chilled water district cooling system, there could be an opportunity for that owner to have a thermal energy storage tank that they could use to provide financial benefit to them. What's interesting about that picture right in the center of the San Antonio Airport, that is our oldest thermal energy storage tank. That tank there is almost 40 years old. The airport still uses the tank every day, and they use it to cool their new terminal building that they built about 10 years ago. It was originally installed almost 40 years ago for just pure energy savings. Now they use it instead for that additional cooling for the new terminal. And every one of our thermal storage tanks we've ever built are still in service today, which speaks to the longevity of this type of technology. Here's a couple of case studies I'm going to show you. This is a small college campus, Bucknell University in rural Pennsylvania. They were looking at expanding their campus, and so they were considering, do I add more refrigeration equipment or do I add a thermal energy storage tank to my campus? And they chose to not add additional chiller equipment, but instead they added a 900,000 gallon thermal storage tank to their campus. And by doing so, they reduced their electric demand by 1 megawatt on their campus. The blue line represents the electric load after the thermal storage tank was added to their central plant. The red line represents the electric load prior to having their thermal storage tank. So you can see that they had a permanent electric load reduction of 1 megawatt of power, and after they added their thermal storage tank, and the tank and the cooling water that was stored in there provided that additional cooling capacity for their expansion. So it provided the cooling for the expansion without adding more chillers and permanently reduced their electric load. Very similarly, this is a college campus in Florida. They were looking at expanding their campus. They also chose to add a thermal storage tank. This was a 3 million gallon thermal storage tank instead of adding more chillers. But the reason I like to show this example is that in Florida, in the wintertime, they actually have 2 peak periods of time that they are trying to avoid energy use. There's a morning peak period of time, which you can see here is between 7 and 9 in the morning, and an afternoon peak period of time. And in this representation, the red and blue lines are the electric load and chilled water production at their central plant. So you can see it trail off and go to nearly nothing during the morning peak. Then it rises up again during the afternoon, and so the chillers are on, producing more cold water, until they're trying to avoid another afternoon peak, which happens between 6 and 8 in the winter. And so during those peak periods of time, and when that chill water production is dropping off at their central plant, that's when they're using the cold water from the tank to provide that cooling for that campus. And it had a significant energy cost savings benefit of over $700,000 a year to go with that type of thermal energy storage tank. But there's many other types of examples of those type of systems that we've built for lots of different applications. If you visit our website, you can see a lot of those project profiles are available for viewing and download from our website. When you do visit our website, you'll see that we build what's called a concrete type thermal energy storage tank. That allows an owner to even partially bury the tank. Because it is concrete, it can be partially buried or differentially buried in the ground. It could also be fully buried in the ground. Because it is concrete, we've buried some of our thermal energy storage tanks completely underground. On the left-hand side, you're looking at a fully buried thermal storage tank under the track and field at the University of Southern California. On the right, you're looking at a 2 million gallon thermal energy storage tank under Mount San Antonio College's parking lot. So the students park on top of that thermal energy storage tank at that college campus. Just a little bit about the design of our thermal energy storage tanks. As I mentioned, we specially designed the diffuser type piping inside of the tank. And this specially designed piping allows the chilled water to slow down as it enters and leaves the tank so that it's near laminar flow and doesn't mix up the cold water at the bottom of the tank with the warm return water at the top of the tank. We also can provide a radial plate type diffuser system in the tank. similar type principles where we want to slow down that flow, stratify that chill water in the tank. So we're capable of designing either type of those diffuser systems within our tank, and typically we decide which is the most beneficial based on the flow rates going through the tank. It's also important that all of the tanks that are built are watertight, because there's chemical treatment in chilled water systems there's usually a biocide and a rust inhibitor in small concentrations within chilled water. We don't want that type of chemical to be leaking out. So all of our tanks are built watertight. And with our concrete tanks, we build what's called a pre-stressed concrete tank that has a precast concrete core wall. This is a steel reinforced concrete core wall that's cast on site, which is about 5 inches thick. We have a steel diaphragm within that concrete tank that will prevent any water from leaking out through the wall of the tank. We then have miles of steel pre-stressing wire and shotcrete over the outside of that steel diaphragm. So we will be wrapping the tank in miles of this pre-stressing wire, pulling the walls into compression to provide the structural and seismic rigidity of the tank. And we'll have multiple layers of those wires and shotcrete that will encase all the steel components in a wet concrete mix. We'll also design seismic restraints into the tank. Depending upon where we're building these tanks in the country, there's different seismic conditions. And these are steel cables that are cast into the concrete floor and then wrapped and encased in shotcrete on the outside wall of the tank. So in case there is a seismic event and the walls start to shake, it allows some movement, but it does not allow the walls of the tank to slide off of the tank floor. And we'll also have a flexible floor wall connection. This is a flexible PVC water stop. Half of it is cast into the floor. The upper half of it is cast into the wall. And it allows that small amount of movement in the wall in case there is a seismic event, but also acts as a barrier to prevent any water from leaking out of in between the wall and the floor joint of the tank. So all of our tanks are built watertight and in this manner. And we can also build a tank with a flat roof or a free span dome roof. So on the left-hand side, you're looking at a column-supported flat roof thermal storage tank. This is that 2 million gallon thermal storage tank that was eventually fully buried under the parking lot, but it is column supported, so it has the structural integrity to hold up a fire truck if it were to park on top of it. On the right-hand side, if it's an above-ground tank, typically we will build a free span dome roof, so there's no columns supporting that roof inside. It's just a domed roof where the weight of the roof is supported off of the walls. And then any of the walls surface area that is exposed, we insulate the exterior walls of the tank. So to prevent any heat gain in the tank, we will epoxy bond polystyrene board to the outside of the tank wall. And then the very outside surface of that insulation is coated with a cement-like coating to give it a very hard and sturdy outside surface to that insulation. So that any of the wall surface area then will be insulated to prevent that cold water from heating up. And we have many ways to economically enhance the exterior of the tank. This is the tank that was built in downtown Raleigh. This was, they wanted their tank to look more regal and to match the nearby structures. This is the one at the University of Texas. They wanted their tank to match the color scheme of their nearby academic buildings. This is the thermal storage tank at Cypress College, where the architect wanted this lattice pattern to mimic the lattice pattern that they had on their exterior stairwells that were already on the campus. So they wanted the tank to have a similar type of pattern on the outside. So these are all ways to enhance the outside of the tank, and even to the point of a faux brick type look on the outside of the tank. So you're looking at the 3 million gallon tank at the University of Central Florida, where the outside cement-like coating on the insulation was actually troweled on through a stencil that gave the effect of a brick on the outside of the tank. And you can see that the brick color was intended to match the nearby red brick buildings. And we can mount solar panels or equipment on top of the tanks. Also, here's an example of some solar PV on top of the tanks with some pumps. And from that point on, I'm going to go into now how we would size the tank. This matrix is an example of the volume of water that would be needed in a thermal storage tank, depending upon the ton hours that were required to be stored of cold water and the chilled water temperature difference in the system. So on the left-hand side, the y-axis is the example of different amounts of ton hours in the tank. And across the x-axis is that chilled water difference between the supply and return water. So as an example, if an owner needed 10,000 ton hours of storage capacity in that tank, and they had a 12-degree differential between their supply and return water temperatures, they would need about a 1.3 million gallon tank. But if they had a 16-degree delta T in their chill water, still needing the 10,000 ton hours, now they only needed a 1 million gallon thermal storage tank. So they needed a smaller tank. So anytime engineers or owners are looking at a thermal storage tank system, it's always prudent for them to look at how they can increase the delta T of their chill water system, increase that differential between the supply and return temperatures. That will help reduce the size of the thermal storage tank that will be needed for their system. I'm now going to go through an example. This is a real-world example on a project that we're working on with an owner in Reston, Virginia. But this type of application is one that is common across the country. The owner is looking at adding a chiller to their campus. They're replacing a chiller and a cooling tower at their campus. And it's a 1,000-ton electric chiller with associated equipment. And they're also consider, instead of that refrigeration equipment, can we just add a thermal energy storage tank to the system? So it's a question about a 1,000-ton chiller versus a thermal storage tank. So in Reston, Virginia, a 1,000-ton chiller and associated equipment, that will run the owner about a $1.7 million to install that equipment on their campus. And this is a very a conservative amount. It probably is going to be a little bit more than this cost, but this is the numbers that the owner wanted to work with in their analysis. So 1,000 tons of chiller capacity, $1.7 million to install it. So comparably, the thermal storage tank size for that system, here you see it would be about a 10,000 ton hour requirement. And that's because they have 1,000 tons of cooling. That's what they need. And their peak period of time is a 10-hour peak period that they want to shift their electric load. So 1,000 tons, 10 hours, that's how we get the 10,000 ton hours. And their chilled water system had a delta T of 14 degrees Fahrenheit between their supply and return temperatures. For that size system, they would need about a 1.1 million gallon tank. And I'm showing you example dimensions of that tank, roughly 70 feet inside diameter by 40-foot water depth. But we can build that tank in any custom circular size that would fit on that campus. But a rough order of magnitude of cost for that system is about $2.1 million for that tank. That includes the thermal energy storage tank at $1.265 million, an allowance for the site work to prep the site for the tank, an allowance for all the other work outside of the tank, the piping interconnections that are required, the instrumentation and controls, and the engineering of the work outside of the tank. So that's how we come up with the $2.165 million. So as I'm comparing now the chiller to the thermal energy storage tank project, you can see that the tank is going to be about $460,000 more than the chiller and associated equipment. But with the thermal energy storage tank and based on Virginia's electric rates, the owner is going to probably save about $130,000 a year on energy costs alone. And in just a very high level, simple payback, that's about a 3.6-year payback that even though the tank is a little bit more expensive, in less than 4 years, it'll pay for itself and continue to pay for itself for as long as they continue to use that tank. With the additional benefits of there's lower maintenance costs because now there's almost no maintenance with the tank, but there would have been a lot of maintenance with that additional chiller and cooling tower. Plus, they have the resiliency of all of this large reservoir of cold water on this campus for either backing up their central plant system or helping put out a fire. So if you're looking at projects and considering thermal storage, or the owner would like to look at projects, we can help with budgeting for sizing a thermal storage tank and estimating the cost. And for doing that, all we need is this information. How many ton hours and what is that chilled water delta T of the system? And with that information, we can provide a tank size and budget estimate for you and for that owner. And as the project moves forward and as a more detailed estimate is required, we will eventually need this other information. We'll need to know if the tank is going to be above ground or below ground. Are there any other site constraints that we need to be aware of? What are the soil conditions? What type of exterior enhancements does the owner want to have for that tank? And any other type of information that will be helpful at really dialing in what that cost will be. But this is an example of the information that will eventually be required for that project. With that, I'm going to pause here and see if there's any questions that I can answer at this time.
We do have one. What is the oldest tank you've developed or installed that is still in service today?
That is the tank at the San Antonio Airport. It is going on its 39th birthday this year, 39th birthday, and they still use it every day.
Great. And then we did have another question here. Can you kind of go more in depth on any maintenance that's required for these tanks?
Sure. let's just look at a typical tank, what it looks like. For our tanks, you're looking at an example of one on the lower picture. There is no maintenance regarding the integrity or performance of the tank. There's no maintenance required because we build our tanks out of materials that will not degrade or corrode over time. All the metal components are encased in concrete. All the piping components are materials like PVC or FRP that are going to be not corrode over time. So the types of things that are required annually for a tank would be a very high-level inspection by the owner. It does not have to be a certified inspection. The inspection could just be a visual inspection where you walk around the tank and verify all the insulation is still intact. It wasn't bumped off by perhaps someone who's cutting the grass. Also, we recommend climbing up the ladder. All of the tanks have a ladder up the side and an access hatch on the roof where the owner can look inside the tank and verify there's nothing unusual floating in the tank water. So that type of annual inspection probably takes about 30 minutes, and we would recommend the owner do that every year. Then maybe every 5 to 10 years, it's probably a good idea that the owner does hire a certified dive team to go inside the tank and go in there with a GoPro, videotape what they see inside the tank, and verify all the components are still in place. While they're in there, they can go to the bottom of the tank and they can look to see if there is sediment building up in the bottom of the tank, because with a chilled water system that has biocides inside the tank, those biocides are killing off microorganisms. And because the tank is built to be a big settling chamber, it slows down the chill water flow, these dead microorganisms will naturally settle to the bottom of the tank. And over many years of time, there will be a silt or sediment that is going to be building up in the bottom of the tank, and it's largely due to these dead bugs that are going to be building up in there. So when the diver is in there and while they're inspecting, if they see that there is sediment building up, they can simply vacuum that off the bottom of the tank. So that's a type of maintenance that may be required for a tank.
I think you answered one of the other questions that somebody asked, which was what type of water treatment is needed, unless you want to go more in depth on that one.
Yeah, we're not water treatment experts, so we would leave that up to the water treatment experts. Typically, if an owner has a chilled water system, they already are working with a chemical treatment expert. And that chemical treatment expert will recommend a biocide and a rust inhibitor in their chill water system with or without a tank. So when a tank is being added to an existing system, the owner will notify that chemical treatment company. They will then decide to either adjust or change the chemicals inside the tank inside the system, for the tank when it's added. But there will be a biocide in there, and there will be a rust inhibitor in that chill water system. But again, we would recommend the chemical treatment company make that adjustment with the owner, and that's not something that any tank builder is really an expert in.
Okay. I know that Lonnie also has a question. I think he's going to unmute himself here in a second. And Lonnie, are you there?
Yeah, can you hear me?
Yeah.
Are there any real advantages to the ice systems other than the smaller footprint?
Yeah, well, ice systems are a great thermal energy storage type system because there's thousands of them out there. So they have a long track record of being a good thermal storage type system. And the main reason is the one that you just hit on, Lonnie, where you're storing the energy in a ice phase, which can store more energy in a smaller volume. So if you don't have the room for a very large chill water tank, ice is a great alternative for you. However, there are some things that work against you with ice. It requires a chiller that can cool water down to that temperature. There is going to be a brine solution, so there's going to be other chemicals that'll be in a portion of the system. It's a little bit more perhaps complex to manage, but not out of the ordinary. These are systems that are proven and used daily and are very successful at thermal storage. The only other advantage, Lonnie, that you asked about, other than just space, would be that in very small sizes, they will be a lower cost option than chilled water tanks. But the opposite is true when the systems are very large. When it's a large type campus system, it's usually less expensive for a chilled water system than an ice system. The tanks become very much lower in cost as they get bigger. And then one other advantage for ice that you might, the owner might want to consider is you can provide colder water to the system. Instead of utilizing 40 to 45 degree supply water for cooling, you could actually have a colder water, which would include this brine type solution with the ice system, and you could cool at lower temperatures, which could help on the dehumidification side. So space is the number one reason. If it's a very small system, like a small building, ice is another good example of where we're coming to play, or a low temperature, a very low temperature dehumidification type application.
But if you have to use the propylene glycol, you're going to lose 10% on your power, right?
Correct. You're going to pay an energy penalty with ice, no matter what you do.
Yeah. Thanks.
Mm-hmm. We have a good amount of questions here, so let's see if we can get through them. So another one we have is you touched a little bit on building automation telemetry, measurement of the tank. What points do you find useful to capture?
Yeah, inside the tank, I'm trying to get back to my picture. Inside the tank, there are temperature sensors mounted vertically in the tank. So that's absolutely essential to the keeping track of the amount of cold water and warm water in the tank. So those temperature sensors that are mounted vertically are important. And the only other sensor inside the tank is a level sensor. So there's a level sensor that is on the tank that is measuring the water depth. Even though this tank is part of the closed loop system, it is an atmospheric tank. So you're going to want to know the water level in the tank, because if there is a leak out on the campus, a leak in their chill water system out on the campus, the first thing and the first warning that the owner will have is the water level in this tank is going to start to go down. And so that sensor can be their early warning system saying that there may be a leak somewhere out in the system. You may want to check that before you start draining all the water out of your chill water system. So those are the two types of sensors that are in the tank. There's the temperature sensor and the level sensor in the tank. And then there's the typical sensors that you would have in any central plant system, where you would be measuring chill water flow rate through pipes, temperatures in pipes, valve positions, and so those types of instrumentation that are typically in a central plant would also be used in a thermal energy storage type system.
Discussed cost a little bit, but can the cost of installation for an underground tank be combined with the cost of installing an underground rainwater harvesting tank?
They would be two different tanks. They would be two different systems completely. Because the chilled water tank, the thermal energy storage tank, is always filled with water and is always filled with chill water. It would not be beneficial for the owner to fill and drain a chilled water thermal storage tank, because that's a costly endeavor to refill the tank and chemically treat it every time you would do that. So those two bodies of water, rainwater or stormwater retention, that would be a different type of tank. Not a different type. It could be a concrete tank like the chilled water tank, but they would be two separate tanks and just be used for two distinctly separate applications.
We got 2 or 3 more questions. Let's see if we can get through these. So does on the tank walls have to be changed as the estimated useful life for installation is much less than the actual tank structure? And if not, would it make sense to do so as we are constantly coming across better material with thermal capacities? Is that?
Yeah, so the insulation thickness on the outside wall of the tank is designed specifically to ensure a limitation on the amount of heat gain to the chill water inside. So all of these tanks that you're looking at here are all insulated on the exterior. And even the tank in the very center, which is our oldest tank, as we've mentioned before, it's going on its 39th birthday, that insulation is original on that tank. And because there is a cement-like coating over the outside to prevent it from degrading over time. However, if there's reason to believe it has degraded, maybe it's been damaged by something in a way that has pulled off a large amount of it, or for some reason it has degraded and is no longer insulating the chill water, which I'm not aware of any of our systems are like that, but if it did, then yes, that insulation can be removed from the tank wall and replaced with something that is newer in technology, or maybe has greater R value for more insulation value on it. Most of these tanks are all, when we design for that heat gain, they end up being usually around R14. Some of them are a higher R value, but I'm not familiar with any of them having to be replaced.
Okay. And then the last question here. So to make a system complete, doesn't a set of pumps and a valve tree need to be added and thus maintained, albeit they may appear insignificant against the price of the tank?
Yes, in some cases there is a separate pumping arrangement specifically for the thermal energy storage portion of the tank. That is true, but not in all cases. There are some systems where the tank is incorporated and there are no additional pumps required. There's additional valving required inside the central plant, but not additional pumps. we're experts in the tanks. The tanks that you're seeing here, we're experts in designing these tanks. Our expertise is not in the primary, secondary, or tertiary pumping systems and how they operate. I would defer to engineers who are more experienced in those type of systems to support you or the owner when they're considering a thermal storage tank.
So Guy's email is on the screen. Also, the email that many of you are familiar with, webinars@abraxisenergy.com. I want to thank Guy again for joining us and doing a great presentation and really driving the ship. Thank you, Guy, and thank you, Lonnie, and everybody enjoy the rest of their day.
Thank you, Tyler.